are discussing on the chapter 30, which is the topic for the inductance. So, this topic focuses on how electric currents interact with the magnetic fields, particularly how changing currents can induce voltages in the circuits. So, understanding this is because it is important. It has a role in the electric devices, the power systems, and electronic circuits that we have in our everyday living. So we have the learning outcomes in this chapter or discussion in which we are expected to understand the concepts of mutual inductance, as well the self-inductance and the inductors, as well as how energy is stored in magnetic fields. So we also examine different types of the circuits, including RL circuit, LC circuit, and LRC circuits, and analyze their behavior. So next slide is the introduction to inductance. So inductance refers to the property of a electrical conductor. So, or a circuit that opposes changes in current. So, this opposition occurs because a changing current produces a changing magnetic field. So, this in turn induces a electromotive force or EMF. So this induced EMF always acts to oppose the charge in current following the Lenz's law. So next slide is the mutual inductance. So mutual inductance is important in a practical application such as transformers, wireless changing systems, and the communication devices. So it allows energy to be transferred from one circuit to another without a direct electrical contact. Next is the self-inductance. So self-inductance refers to the ability of the coil or a conductor to induce a voltage in itself. So, when the current flowing through it changes. So, this induced voltage opposes the change in the circuit, or in the change, opposes the change in current. So it makes harder for the current to increase or decrease rapidly. Next slide is self-inductance in the inductors. So a device designed specifically to have a certain amount of self-inductance is called a inductor. So inductors are commonly used in electrical circuits to control current flow, store energy, and filter signals. Next slide is the energy stored in a magnetic field. So establishing a current in inductor requires energy. So this energy is not lost but stored in the magnetic field created around the inductor. So as long as the current continues to flow, they the energy remains stored in the magnetic field. Next is the magnetic field energy. So when a current decreases, the magnetic field collapses and the stored energy is released. So released back into the circuit. So this explains why inductors can resist sudden changes in the current and can produce high voltages when the current changes rapidly. Then we have the RL circuit. So an RL circuit consists of a resistor, and an inductor that connected together. So usually with a source of electromotive force or the EMF, so when the circuit is switched on, the current does not immediately reach its maximum value because the inductor opposes the change in current. Next is the time constant of the RL circuit. So the ratio of an inductance to resistance, or L divided by R, determines how quickly the current build up. So this quantity is called the time constant of the circuit. So a larger time constant means the current takes longer to reach its final value. Next is the LC circuit. So an LC circuits contains only a inductor and a capacitor. So unlike the RL circuits, this type of circuit shows oscillating behavior. So the energy continuously transfers back and forth between the electric field of the capacitor and the magnetic field of the inductor. So that's it for the LC circuits. And we do have the oscillations in LC circuits. Oscillations in LC circuits. So the oscillation in LC circuit occur because energy is conserved and alternates between the capacitor and the inductor. So this principle is used in radio tuners and the signal generators now. So move on to the LRC circuit. So an LRC circuit includes an inductor, resistor, and a capacitor. So in this type of circuit, the presence of the resistance causes the oscillations to gradually decrease over time. So this behavior is known as the damped oscillations. So we have the effect of resistance in the LRC oscillation in the LRC circuits, I mean. So as the resistance increases, the damping effect becomes stronger. So if the resistance is very large, the circuit becomes overdamped, meaning oscillations no longer occur. So the frequency of oscillation depends on the values of L, R, and C, or the inductor, the resistor, and the capacitor. It contains the inductor, the resistor, and the capacitor. So that's for the discussion on the chapter 30. So in conclusion, the inductance plays a crucial role in the electrical circuits by controlling current changes and storing energy in magnetic fields. So understanding this, or like the learning the mutual inductance, self-inductance, and different circuit behaviors help us better understand how many electronic systems function in real life.